Alright guys, this is going to be a very long video, so we're just going to jump right in. Make sure you have your paper and something to write with. Alright, our first objective is we need to know what electrical energy is, and we need to be able to describe the sources of electrical energy. So electrical energy is electricity is just the movement of electrons. Okay, electrical energy is the movement of electrons. Electrical energy can come from many sources. It could come from water or wind. In both cases, hydropower, water power, is used to turn turbines that create clean electrical energy. Green energy, remember, green energy is energy from sources that do not cause pollution. We could get electrical energy from the sun. We've all seen solar panels on people's homes, and even here at school we have a solar panel which captures the heat energy and transforms it into electrical energy, another green source because it doesn't pollute the earth. We could get electrical energy from nuclear sources. Remember that nuclear energy is the energy that's within the nucleus of atoms that we get either when the atom splits or when it fuses. So again, this is another source of electrical energy. And the one that we've experienced or that we've done in class, we could get electrical energy from chemical sources such as batteries. Remember that a battery goes into a device and it completes a circuit which starts the flow of electrons. All right. A circuit is a closed path through which electrons can flow. All right. So keyword here is closed path. It must be closed. If it is open, then electrons will not flow. And we'll talk about the two types of circuits. There are series circuit and parallel circuits. Before we do that, let's look at the circuit components. A straight line represents a wire. You have this on your paper, so I'm going to go really fast. Squiggly line represents a resistor. A circle with an X in it, that represents a light bulb or any kind of load. Could be something else. A cell is represented by a short line and a longer line. A battery is represented by two of those, and a switch it's like an open line segment. When it's closed, then the circuit is closed, and so electricity can flow. When it's open, the circuit is open, so it's not a closed path anymore, it's an open path, and electricity will not flow. So think of our light switch. When our light is on, then that circuit is closed. So when you flip that switch up, what you're actually doing is closing a circuit. When you flip it down to turn the light off, what you're actually doing is opening a circuit. Alright, so we must be able to explain the two types of power. We have alternating and direct current. Alright, alternating current is a type of electricity that we get from wires. All right, this can travel over long distances, so anything that you have to plug in is alternating current. And in alternating current, electrons can switch directions in which they're going. They could go forward, they could go backward. All right. Direct current, however, can only travel short distances, and direct current is the electricity we get from batteries. All right, and okay. So series circuits, there are two types of circuits. There's series and parallel. All right. Series circuit, current travels in a single path from negative to positive, and one break stops the flow of electrons. Okay. So if you have, for example, in this one, if you have a circuit that has three loads, okay, if one of these are removed from the circuit, it stops the flow of electrons, and so the everything will stop working. All right. In a in a circuit like this, each device receives a fraction of the total voltage. So as you add more things, it gets dimmer. Okay. These are examples of series circuits. Again, if one of these parts are removed, then the whole thing stops working because electrons stop flowing. Okay. Parallel circuits, on the other hand, electrons have multiple paths in which they could flow. All right, so a break in the circuit doesn't stop the flow. So if we have 10 things strung up, so think of your Christmas tree. So some are in circuits, some are in parallel. The ones that are in series. The ones that are in series, when one light goes out, the whole thing goes out. That's a series circuit. The Christmas tree that are in lights that are in parallel, right? When one goes out, the rest of them still work because they have other ways to get there, right? So current takes a path of least resistance, and the biggest light would be dimmer because they're all getting the same amount of energy. So if you're bigger, you're still going to get the same amount. So if you're bigger and you need more, then you're just going to be a dimmer light. Okay? And when you add more lights, then there's no change in dimness. Okay? These are all examples of parallel circuits. Again, if this light, let's say, goes out, then electrons can choose a different path to go. They could go down here, and these two will still work even if this one is out. Okay? All right. In our homes, we have a combination of circuits. Okay? We have series and parallels. Sometimes when you're at home and you start to plug up a bunch of things, you can see your lights get a little dimmer, and that'll give you an idea as to what kind of circuit that is. In our homes, we also have safety features such as circuit breakers, which are bimetallic strips. So when it gets hot, it bends, and then it completes or breaks a circuit, right, to stop the flow of electrons. Not completes or break, but just breaks a circuit to stop the flow of electrons. All right, we need to be able to describe the types of simple machines. All right, simple machines are devices that are used to help make work easier. Okay, and they do this in several ways. They either transfer a force, all right, or change the direction of the force, or increase the magnitude, or increase the distance. All right, again, guys, if I'm talking too fast, just pause the video, record what you need to record, and then press play. Okay? There are 6 main types of simple machines. There are the levers, wheel and axle, pulley, inclined plane, wedge, and screw. And remember, the way simple machines work is that they help to make work easier. And the way they do this is either they are transferring a force from one place to the next, changing direction of the force, increasing the size of the force, or increasing the distance or speed of the force. So as we look at each simple machine, I want you to think of, how is this making work easier? What is it doing to make work easier? All right, a lever is a rigid bar that rotates around a fixed point called a fulcrum. All right, it could be straight, it could be curved. All right, so there's a point. So let's think of a seesaw. The point in the middle that the seesaw rotates around, that's the fulcrum, where there's a point at which you're applying force, and then there's a point at which you're lifting a load. Okay? So a lever has both an effort and a load. And these are all examples of different types of levers, right? And Remember that simple machines, they have little or no moving parts. And as you look at these simple machines, they could be more than one types. For example, the axe. The axe is a lever, but it also has a wedge at the top of it. All right. The wheel and axle is a simple machine that consists of a large wheel that's rigidly secured to a smaller wheel. If you think of a doorknob, one of the round ones, that's an example of a wheel and axle. This is one of the things that helps to transfer force, right? If you've ever lost the big part of your doorknob, you could recall how hard it is to turn that little part. All right, so other examples of wheel and axle are cars, wheelbarrows, and motorcycles. A pulley consists of a groove wheel that turns freely in a frame called a block. All right, so a pulley a pulley is one of those things that help to change the direction of a force. Okay, so again, we're thinking, what is it doing to either the force or the distance to make work easier? And we'll look at the formula for work in a few. All right, an inclined plane is an even sloping surface, right? And it makes it easier to move a weight from lower to a higher elevation. So think of lifting a box versus pushing it up a ramp, right? It's a lot easier to push a ramp. So let's think of our washing machine, something heavy, all right? You could lift it from point A to B, right? Or you could push it up an inclined plane. If you choose to lift it from here to here, right, it's going to be a lot heavier. Probably can't do it by yourself. Might need somebody to help you, okay? But should you decide to use an inclined plane, for example, a ramp, and increase the distance, you're pushing it for longer, but now you can actually do it by yourself, maybe, if you're strong. All right, so a simple machine is just, it uses a variety of ways to make work easier. All right, so here's an example of a ramp at work, all right? When you look at this example, look at what's happening with the force each time, okay? So the longer the distance that you make, the less force you apply. But the work that you're doing is actually the same. You're doing the same amount of work. So you decide, do you want to exert 17 newtons of force, right, to do 8.82 joules of work? Or do you want to exert 9.8 newtons of force to do the same amount of work? Simple machines make work easier. Okay? All right, the wedge. The wedge is a modification of the inclined plane. Wedges are used either as separating device or holding devices. Right? Good example of a wedge is an axe. So again, an axe is not just a lever, but it's also a wedge. All right, the screw is a modified version of an inclined plane. It's kind of hard to see, right? But if you look closely at a screw, you could see that the threads kind of create like this circular path, and it allows it to go into something a lot easier, right? Other common examples, more obvious examples, are a water bottle or the bottom of a light bulb. All right, so these are examples of a screw. All right, our next objective is to be able to explain mechanical advantage of a simple machine. Okay, mechanical advantage is how many more how many more times, how many times more force can you get out of a simple machine is what it is, all right? And again, simple machines increase our mechanical advantage, all right? So a mechanical advantage of 6 means that the machine is putting out 6 times more force than you were putting in, okay? All right. Our next thing is we need to be able to explain the efficiency of a machine. All right, the efficiency of a machine is the input force times the distance, all right, and that should be equal to the output force times the distance. All right, the input force times distance should be equal to the output force times the distance. No machine is 100% efficient, because a machine, as we know, consists of moving parts, and where things are in contact, there's friction. So you're always going to lose some force, right, to friction, right? So the comparison of the work that you put in over the work that's put out is called the efficiency of a machine. And again, remember, no machine is 100% efficient. All right, we need to be able to describe and identify work. All right, work is done when a force acts upon an object and it moves in the direction that you're applying the force. All right, if we were to put that in a formula, work would be equal to force times distance or displacement. Let's go with displacement. Work is equal to force times displacement. Okay? Work is measured in a unit called joule. And 1 joule is the same thing as a Newton meter. A Newton meter is what you get when you multiply force times distance. And again, remember, it's the same thing as a joule. All right. How much work is being done by the weightlifter below that applies 500 newtons of force, lifting a mass 2.5 meters. So again, remember, work is equal to force times displacement, okay, which is F times D. So your F is 500, your D is 2.5 meters. That's going to be equal to 1,250 joules, okay? How much work is being done by the weightlifter below that applies 1,000 newtons of force but does not move the mass? Okay, let's look at what we have. Force, they told us, is 1,000. Distance, they told us that he does not move it. Therefore, the distance is 0. Work is equal to F times D. 0 times anything is 0. All right. So again, because he did not move, because he did not travel a distance, no work was being done. Okay? So he did work when he picked it up, but if he's just going to stand there and hold it all day, then that's not doing scientific work. All right, so you need to be able to identify work in scenarios. So this is what it will look like on a test. So a mouse, a teacher, a lecturer in her class, is that work or not? Okay, a mouse pushing a piece of cheese with its nose across the floor, is that work or not? Surprisingly, right? A teacher lecturing her class, not work. Okay, she's not moving, she's not pushing anything, she's not applying a force over a distance. It's not work. Okay, a mouse pushing a cheese with its nose, the mouse is applying a force, yes, and it's moving something through a distance. So yes, that is work. So the mouse is doing more work than me. Okay, again, this is what we just said. Because the mouse is using a force to displace an object in the same direction, then yes, he's doing work. right? A scientist delivering a speech to an audience of his peers, is that work or not? Okay, I want you guys to write in pencil whether you think these scenarios are work or not, and then I'll give you the answers in a few. Okay, so just take a few moments to go ahead. You might want to pause it. Go ahead, read the scenarios. Tell me if you think these scenarios are work or not. Okay, so I would pause it if I were you. All right, scientist delivering a speech, not work. He's not pushing anything. He's not applying a force. He's not moving a distance. Okay, bodybuilder lifts 350 pounds above his head. Yes, that's work. He's applying a force. He's moving an object a distance. All right. Mother carrying her baby from room to room? No. Okay, because she is not applying a force to the baby in the direction that the baby is moving in. So technically, yes, she's applying a force to hold the baby, but unless she's lifting that baby above her head, it's not work. Okay, so you have to be moving in the direction that you're applying the force in. Okay, father pushing a baby in a carriage. Yes, that's work because he's pushing the baby a distance. He's applying a force to move the baby, and the baby's moving in that direction. Okay? Same thing, a woman carrying a woman carries groceries to her cart because she's carrying it, right? Because she's not pushing it, right? It's not considered to be work because the force and the distance are not going in the same direction. And that is it. Thank you, guys. See you in class.